Hello everyone and welcome. My name is Tanuj Arora. I am the product manager of Ethos U55 NPU. Joining me today is my colleague Pareena Verma, and I'll let her introduce herself.
Hi everyone, I'm Pareena Verma. I'm a Principal Solutions Architect in the Development Solutions Group at ARM. Thank you for joining us for this talk at DevSummit 2020. I'll let Tanuj kick off the first half of this presentation. Back at you, Tanuj.
Thank you, Pareena. Today, we will be talking about benchmarking and performance analysis of machine learning workloads on ARM's Ethos U55 NPU. Before we get into the details of benchmarking on U55, let's start with a quick introduction of the NPU and its capabilities. Ethos U55 is a new class of machine learning processor called a microNPU. It is specifically designed to accelerate machine learning inference in area-constrained embedded and IoT devices. The U55 is a configurable IP that is paired with a Cortex-M processor, and it allows designers to target a wide variety of AI applications with 4 different configurations: 32, 64, 128, and 256 max per cycle. This allows for U55 to be used in different use cases targeting various performance points. U55 is connected to the memory bus and uses the existing system SRAM and flash memory. It comes with a high-performance, high-efficiency Mac engine to accelerate a fixed set of high-compute operators in hardware. Other operators execute on the attached Cortex-M. In the first version of this IP, we're supporting 4 different Cortex-M processors: Cortex-M55, M7, M33, and M4. Ethos U55 supports 8-bit integer weights and 8 and 16-bit integer activations. Ethos U55 also supports weight compression and has a weight decoder for on-the-fly decompression. Compressing weights is extremely important in embedded systems as there is limited amount of memory available. There are 2 major benefits here. One, it allows for larger networks to be stored on a device. As neural network weights are a big strain on flash capacity, compression reduces the amount of memory required to store the network, hence allowing execution of networks that wasn't possible before. Second, compression not only allows for execution of more networks, it provides higher performance for executing those networks as well. Fully connected and RNN LSTM layers are typically weight load bound, and compression speeds up the execution as there are less weights to be fetched from the memory. So what networks can be executed on Ethos U55? As mentioned before, Ethos U55 supports a fixed operator set. We looked at many popular networks available in the market and came up with a list of compute-heavy operators that made sense to be accelerated in hardware. Any network that is comprised of these operators can be executed completely on Ethos U55. For example, DSCNN-L, which is a keyword spotting network, ResNet50, MobileNet, which are image classification networks, Deep Speech, Wave2Letter, which are speech recognition, just to name a few. Please note this is not a comprehensive list by any measure, and these are only a few examples that I'm quoting here. Any unsupported layers are executed on the CPU and accelerated in software through CMSysNN. CMSysNN is a library of optimized low-level kernels for Cortex-M CPUs. It can be called from either TensorFlow Lite Micro or bare metal implementations. It is an open source library available with an Apache 2 license, and we do quarterly releases to keep it updated with popular operators that require acceleration. I would encourage you to download it and run a neural network using CMSysNN on your favorite Cortex-M. Now let's spend a couple of minutes understanding the software flow of accelerating neural networks on a combination of Cortex-M plus Ethos U55. On the left is the host where the network is compiled offline. The right side of the diagram here is the target device where the network is being deployed. The process starts by training or acquiring a TensorFlow model that is to be accelerated. The model is then quantized to 8-bit integer and converted to standard TF-Lite flat file format. The optimizer tool provided by ARM reads this TF-Lite flat file as an input and formats it to make it ready for deployment. Once the file has been run through the optimizer, it is deployed on the target device using TensorFlow Lite Micro runtime. TensorFlow Lite Micro is an offline runtime created to execute within the constraints of embedded devices. The flat file created offline contains information on which layer of the neural network executes on Ethos U versus the attached Cortex-M. The layers supported by Ethos U are accelerated, and the remaining layers execute on the attached Cortex-M. The layers that execute on the Cortex-M can again be accelerated through the CMSysNN software library that I just talked about. Otherwise, if those kernels are not available, the fallback to TensorFlow Lite Micro reference kernels is always there. Let's talk about TensorFlow Lite Micro in a little more detail. ARM has been working in collaboration with Google on the development of TensorFlow Lite Micro and is making significant contributions. TensorFlow Lite for microcontrollers is a version of TensorFlow Lite specifically designed to execute machine learning models on microcontrollers and embedded devices with only a few kilobytes of memory. TF-Lite Micro doesn't require any operating system support, standard C or C++ libraries, or dynamic memory allocation. The core runtime fits in 16 kilobytes on an ARM M3, and with enough operators to run a speech keyword detection model takes up to a total of 22 kilobytes. These are only examples, and there are demos that consist of simple vision and voice networks that you can start with. There are over 50 operators that exist today, and that list is growing quickly. Looking at the NN optimizer tool in a little more detail, this tool is provided by ARM to format a neural network for the Ethos U NPU. It takes a trained neural network in a TensorFlow Lite flat file as an input and formats the network to output a modified flat file ready to be deployed on the target device. After reading the flat file, the tool identifies the subgraphs that can execute on Ethos U and optimizes the scheduling of these subgraphs. Next, the tool compresses the weights to reduce the SRAM and flash footprint, thereby improving performance of memory bandwidth bound layers. The compression, as I mentioned before, is extremely important as it allows for the execution of bigger networks that wasn't possible before. Finally, a command stream is generated for the NPU and the modified flat file is written. We've analyzed many popular networks that are available today and on average see up to 70% reduction in model size and up to 90% reduction in the SRAM required. Here are performance results for a few different networks in Cortex-M and Cortex-M55. The three networks that I'm showing here are DSCNN-L, which is a keyword spotting network, MobileNet, which is an image classification network, and Wave2Letter, which is a speech recognition network. These networks are being shown here as examples, and other neural networks can be executed in a similar manner. As it can be seen here, Cortex-M55 provides a significant uplift over previous generation Cortex-M4 from 5 to 11x in these examples. Now let's add Ethos U55 to the same chart and see how that compares to the results here. All of these networks are completely executed on Ethos U55 and no operator falls back on the CPU. A huge uplift in performance can be seen around 110x for DSCNN-L, 73x for MobileNet, and over 250x for Wave2Letter. Two important points to note here. One, this huge performance uplift also results in a big improvement in energy efficiency. And second, the config being used here is the 128 max per cycle config. There is a bigger config of Ethos U55 available, which is double the number of max and can be used for an even bigger performance uplift. At this point, I'll hand over to my colleague Pareena to take you through the benchmarking section on Ethos U55 virtual platforms.
Thanks, Tanuj, for providing an excellent overview of ARM's microNPU, the U55, as well as the overview of the software architecture in terms of the TF-Lite, the CMSIS, and then libraries that need to be run in the host compiler and cross-compiled with, and then finally deployed onto your target device. So in the next section of the presentation, I'd like to cover how one can develop and evaluate the performance of these neural network models, some of which Tanuj outlined in the earlier half, without having a board or silicon available, and how one can get up and running not only with the software, but also understand the performance of these neural network models. So in this half of the presentation, I will be covering benchmarking the Ethos U55 using ARM's virtual platforms, which use proven technology of models that exist and are deployed by ARM, which are the ARM fast models and cycle models. So we have two abstractions of platforms available for users to run their neural network models on with the Ethos U55. Now, one is the fast model system, and the other is the cycle model system. Before I provide an overview of what the differences in the abstraction of these systems are, I wanted to highlight that both of these systems are architected in a way that they have the same components, the same memory map, so that the same software executable can run either on the fast model system or on the cycle model system seamlessly. So the fast model system, what are ARM fast models? So ARM fast models are program reviewed models. And as their name indicates, they run really fast, can execute millions of instructions per second. And they're extremely useful for software developers to bring up their software early on in their development cycles, even before silicon or boards are available to do that development. They are functionally accurate for software development, and they're extremely great with checking things such as new architecture features, for example, in the Cortex M55. With the Helium technology that was added, if you want to check the porting of your vector instructions, fast models are a great way to do that. Now, the fast model system for Ethos U55, just like the cycle model system, is composed of a host CPU subsystem, which consists of the Cortex M55 as the host CPU, an interconnect, which in this case is a NIC 400, and the microNPU, of course, the star of the show, along with memory, which is an SRAM, and some peripheral to get your input and output messages out on a console. The cycle model system, like I mentioned earlier, consists of the exact same models, the exact same IP. The difference is these models are very detailed. They are 100% cycle accurate. They are built directly from RTL. And they're very useful when you're trying to evaluate how long a particular inference takes to run on the system in terms of the number of cycles. So you can only get that detailed 100% cycle accuracy with these accurate models. Another advantage of using the cycle model system is if you're looking to evaluate some system level performance metrics, such as the bus utilization of your SRAM and memory bandwidth utilization. So to sum up this slide, there are two platforms, virtual platforms available on which you can run your TensorFlow-Lite micro workloads that are targeted to run on U55. One is a fast model system and the other is a cycle model system. So these are the target systems. So now that we've covered the target systems, we'll move on to covering how the software is ported to these systems, which is more or less a recap of what Tanuj said, but we wanted to cover the exact steps of what a user would go through while trying to port their NN model onto these systems. So you start out with a quantized uint8 or int8 TF-Lite model, and we provide two examples with these virtual platforms that are already pre-ported, which I will be covering in the next couple of slides. But the starting point is your TF-Lite model, which is already quantized to uint8 or int8. Then the next step is you use the NN optimizer tool that Tanuj had detailed. you run your TF-Lite model from your previous step through the NN optimizer tool, which creates this new TF-Lite model and has checked for the accelerated operator support and also gives you performance estimations. Now, using the TF-Lite, TensorFlow Lite for microcontrollers framework and the optimization provided by the CMSIS NN libraries, you can start to build up the final executable or the AXF image that runs on these fast and cycle model system that encompasses not only the TF-Lite runtime and the TF-Lite model that you're running, but also information about these underlying target devices. For example, what does the memory map of the system that you're running on look like? Where are the peripherals located for the input and the output? So there's an all-encompassing script provided that easily builds this one executable that runs on your target fast and cycle model system. And finally, once you have your compiled image, you deploy it onto these systems, and then you're able to view the classification results of your neural network model and analyze the performance data that you have got from the cycle model system. So that's really the software flow of how certain examples are ported to the virtual platforms and how custom models can be extended to be ported using the exact same flow. So let's cover the two examples that we've already ported onto these virtual platforms. So early on, Tanuj mentioned a whole slew of networks that would run on the Ethos U55, which in itself is not all-encompassing, but we took one of the popular ones, MobileNet V2, which is an image classification model. It is a convolution neural network. It's been pre-trained with thousands of images in the ImageNet database and can classify objects into thousands of categories. So the first thing we did was we took the MobileNet V2 TF-Lite model that's openly available on TensorFlow, and we ran it through the software steps in the previous outline in the previous slide. In addition to doing that, when you run an inference with this MobileNet V2 model, you also need to give it which is the input image that you would like to classify and run on your target device. So there are several different input images that we passed through MobileNet V2. Here's an example of one, the most popular, the cat image. And sure enough, the cat image was classified into three different categories of the cat, where you can see the classification results on the right. So that is the image classification use case that we ported to the U55. The second interesting use case we ported is a keyword detection neural network model called microspeech, also available on TensorFlow. And this TF-Lite model basically runs an inference where it can detect certain keywords in an input speech data pattern. The keywords are yes and no, or if there is complete silence. So we passed another input data sample file with different keywords, with keywords in it, which actually would detect yes. And as you can see, on running that model, the classification results on the right show that it was classified as a yes with 86% confidence. So these are the two examples that we were able to, very easily provide for developers to get up and running with not only the software flow, but also understand the modeling flow at the back end to get a good feel of the developer experience on someone who is new to ARM's microNPU. Now, once we run these examples, you might ask, that's great, the classification is done. What sort of metrics can you get from running these simulations and running these workloads on the fast and cycle model system? So there are several different granularity of results that you can get to understand the performance. Let's start with the highest level, which is the cycle and the instruction counts. So you can run these workloads on these systems, and right away there's a graphical user interface which you can use to control viewing your simulation results, or you can view them in your command line. where you can view the number of cycles it took to run a particular inference, like micro-speech or like mobile net. You can also easily trade off and compare the advantage of using the Ethos U55 in your system to run an inference. So for example, you can run image classification on a system which has both the M55 and the Ethos U55 versus a system with just the host CPU and no U55. And you can easily grasp the advantage of using the acceleration in the Ethos U55 by comparing the number of cycles that it took for the inference to run on a system with the U55 versus without it. So that was the highest level of analysis. Now there are certain mid-level statistics available as well. You can view details such as the SRAM bandwidth utilization. So the Ethos U55 has two interfaces connected to an SRAM memory, and you can view the activity on those interfaces in terms of the number of the read and the write transactions going out on your bus on these interfaces. And these graphs are available to you as well as the data itself if you want to post-process it in another format and compare the bus metrics while running different simulations with different workloads. And finally, there's very detailed level of analysis available for someone benchmarking on Ethos U55 and doing performance analysis. You can view a breakdown of the number of cycles that it took for each operator to run. For the Ethos U55, of course, it's mapped to a custom operator, so you would get how many cycles the custom operator took to run the inference. If you were running on an M55 system, you would get a breakdown of the cycle count of each of those operators and how long it took to execute. Furthermore, you can get statistics such as the tensor arena usage in your application, like how much of that memory was used for the tensor. You can get insight into several performance counters in the host CPU while running such simulations. You can calculate cycles per second, inference runtimes. You can look at the software instruction traces, and even the hardware architects can go down into the levels of even looking at the waveform activity of the Ethos U55. So there is a broad gamut of metrics available for your analysis, ranging from the high-level cycle and instruction counts to very detailed waveform and traces available from your simulations. So to sum it up, these are the virtual platforms we have available for U55 to not only understand the performance and the benefit of using the microNPU, but also getting a feel of the software workflow of using the NN optimizer, the open source neural network TF Lite engine, the CMSys NN optimization libraries, kernel libraries, and building it all in one place in an all-encompassing format and understanding the performance and the development around the U55. With that, I'd like to thank you all for attending our session, and I hope you found this useful to understand an overview of both the U55, the software architecture, and how you can benchmark it. If you have any questions or any feedback at all, please don't hesitate to send us a question or reach out to Tanuj or myself, and we'd be happy to hear from you and address any and all of your questions. Thank you all for your time.